Okay, I think we're good to go.
Just let one. All right. Yes. Welcome back, everybody. Good morning. I will start sharing my screen. So for the first half hour today, we will finish with the last example of the lithospheric deformation session. But before that, I just wanted to wrap up what we did yesterday with the brittle thrust benchmark. And this is where we all left off. We had a look in paddle view at the density over time. But I also promised you higher resolution results. So this is what we see here. I ran the original benchmark as described in the Badger et al. Paper, and then going down, you will see higher resolution runs. So what is directly very clear is that the interfaces between the different compositional fields become much sharper with resolution. But then what is a bit surprising is, for example, that we have this additional forward thrust here at the front of the wedge. And this can be due to the higher resolution of the boundary layer, but also due to the mesh dependency of the plasticity. And this is what was seen throughout the results of the modeling study. For example, this is one figure from the paper. And this time resolution increases from left to right, and then the different rows represent model results for different softwares. So what we can see here is, for example, in this scale example, is that the location of the shear zone varies a little bit with resolution. Additional shear zones form, and especially if you look at the strain rate field, the width of the shear zone changes with resolution. However, we can also look at the evolution of the model over time. So this time the column is snapshot at 2 centimeters, the second column at 6 centimeters, and then each row is again a different code or a different analog lab here at the bottom. And then what the main difference in evolution is that there are actually like two modes of deformation. So one is a series of thrust pop-ups, like for example here in the top row, and the other show mainly forward dipping thrust, like here. Overall, the model evolution is similar. The models converge to this critical taper of the wedge, but there are variations in the rate of thrust formation, the number of thrusts, the dip angle, and the spacing of the thrust. And these differences are caused by different numerical solution techniques. So these codes used finite elements, finite differences, discrete elements, boundary elements, etc. They use slightly different resolutions, and if they had remeshing methods were also different, but the most important cause of variation was the implementation of boundary friction. So whether they described a force or a thin boundary layer like we did, how they treated this boundary layer, what happened to the particles when they left this boundary layer, etc. So I just wanted to make you aware of that. Now, if you want to extend this model, one thing you should definitely have a look at is the grid resolution, like keep it uniform and at a higher resolution level throughout the sand layer. You could try particles or the volume of fluid method that are also implemented in Aspect, and that would lead to less diffusion of the boundary layer. You could change the time step size. You could change the strain weakening mechanism, like, for example, using only plastic strain. You could expand the allowed range of viscosities, and you could, of course, look at it in 3D, and then you would also have extensional features in there. So what I wanted to give you as a sort of homework yesterday was to try and change the strain weakening mechanism, but I think I will just leave that for you to try in a break or after today's program. But the solution is also to be found in the slides here. Okay, so that was just what I wanted to say about what we did yesterday, and now we'll just make a switch. We will stay at convergent settings, but we will look at a larger scale. And as it will take some time, I would like to ask you to start the model first. So please all go to the session 3 directory and start the model prescribed subduction.
And there was a request in the chat. And Arun had asked whether you can show the calculator and display the results step if you have time. I assume that is for the model that you were discussing.
For the thrust wedge, yeah, of course. Should I do that now? I can do that now. I will stop sharing and I can have a look at the chat. Okay. No. Sorry, I couldn't find the right screen to share, but here we are. So if we open, I think we did this yesterday as well, so sorry for the repetition. Anyway, we have our model over here. This is what it looks at like without the filters applied. Then we click calculator and we sum Q sand with C sand over here. And then we apply another filter, the threshold filter. We set it to minimum of 0.5, apply, and that cuts away all the other compositions. And then we just display the density, rescale, and get the scale out of the way. And then we can play it over time. In principle, we should be able to play it over time. Okay, I hope that explains the process. Then I will go back to the PowerPoint. Okay, so this would have given everybody time to start the model, and I will just continue with explaining what it actually is that we're doing. So like I said, we're sticking to convergent setting, but at the lithospheric scale. So at convergent boundaries, plates subduct underneath another plate, overlying plate, and this can be accompanied by mountain building, volcanism, earthquakes, fluid release, mantle melting, metamorphism, many processes. Today, however, we will stick to the minimum requirements of modeling a subduction process, and that is actually a weak zone that decouples the subducting plate from the overriding plate, a weak layer like crust or sediments that decouples the subducting plate from the surface and allows it to go down, or alternatively, a free surface. And thirdly, something to initiate subduction. So this is like a negatively buoyant slab tip that is already hanging in the mantle, or prescribed plate motions or forces. And with this, we will construct this simple model of intraoceanic plate subduction. So this setup is based on a benchmark effort of Quinquist in 2014 and considered 7 numerical codes and 4 setups that increased in complexity. So the first one is linear viscous rheology, then it adds temperature advection, then the viscoplastic rheology, and then strain weakening. But we will focus on the linear viscous rheology. But just as a teaser, here are snapshots of the viscoplastic case 4. So where we see the slab, basically turning in on itself over time. The setup of the model looks like this. We have a box of upper mantle scale with 3 compositions in there. So there's the overriding plate OP, there's the subducting plate SP, and then there's a crustal layer that turns into a weak zone over here. And then I added these dots because those are points, and I use their coordinates in the input file to prescribe the compositions, so just so you know what they are. Then in terms of velocity boundary conditions, it's actually quite simple. We use free slip everywhere except on the right boundary, where we have an inflow on the subducting plate and then a gradual transition to an outflow of roughly 1 centimeter per year that counteracts the inflow of the subducting plate. So how does that translate to the parameter file? Again, you can open up the file or just follow along with the presentation because I show all the parameters. So this time, again, 2D, but we set the use years in output instead of seconds to true. So we model 15 million years, and temperature plays again no role in this setup. Because the viscosities are basically constant per composition, we don't need an iterative solve. So we use this single advection, single Stokes solver scheme. And then the Stokes solves are controlled by the linear solver tolerance and the number of cheap Stokes solver steps. The geometry model is a box, this time 3,000 times 670 kilometers. And then we do 4 X repetitions to make sort of square elements again. For the compositional fields, we consider 3, like I said. So there's the overriding plate, the mantle lithosphere, and the crust of the subducting plate. And then the sublithospheric mantle is the background. Then for the function constants, I use these AX, AZ coordinates, so the dots in the setup figure. And then this is the expression for the field. So if you want to make this model more complex, this is maybe the point where you start thinking about writing a plugin instead of using this function expression from the input file. But as you see, it can be done. Then because we have inflow on the right boundary, we fix the initial composition on the right. No, we fix the composition to its initial value on the right boundary. And then because temperature plays no role here, we set it to 0 everywhere and, well, fix it on the right boundary where there's inflow. The boundary velocity model, this is, of course, very important. So tangential boundary conditions on the left, the bottom, and the top, but then on the right, we prescribe the X component of the velocity. So the Y component is left free. But we specify on the right boundary this inflow of -5 centimeters per year along the thickness of the subducting plate, gradual transition to 1 centimeter per year outflow. In terms of the material model, we use multi-components. So this is a lot simpler than the viscoplastic material model, but it allows for having compositional fields with different properties, so any number of compositional fields. And in this case, only the viscosity and the density vary between the fields. And because we set the reference temperature to 0, which is temperature everywhere, the density is fixed at these values that we give here, the reference values. Then for viscosity averaging scheme, we take the maximum composition, and this helps when the thin weak zone starts diffusing away, but we really need it. We need its low viscosity to decouple the 2 plates. So let's say we make it the dominant viscosity inside the weak zone. Yes, and then the mesh refinement, this helps us follow the slab with depth while keeping a fixed high resolution in the crustal layer. So we start off with an initial global refinement of 4. Then we do 2 adaptive steps, and they can lead to coarsening or to refinement, but we fix the minimum refinement level at 2. So because we want to have this minimum resolution everywhere. So coarsening and refinement based on the minimum refinement function, but also the viscosity and the composition. So this is what allows us to track the slab into the mantle over time with the resolution. And then this minimum refinement function is just there to make sure that the crust is always refined at the same high level. And then for post-processing, we will obviously output visualization files and then some velocity statistics. So these print the minimum, maximum, and root mean square velocity over the whole domain at every time step. And then the graphical output is written every 500,000 years. All right. I think that it's about 10 minutes, so you should have your model run. If not, you can still have a look at it. You can load the PVD file anyway, and then if you want to reload it, this is possible in this version of ParaView. You just right-click on the PVD file and select Reload Files, and then it will update the file that you have already loaded. What is interesting, or the easiest way to look at the model evolution, is to actually display the viscosity. And you can do that by selecting the viscosity parameter and then click Edit Color Map, and there you can select Use Log Scale. And this is the nicest way to look at viscosity. So I suggest you load the file and have a look at what the slab's doing, like advancing, retreating, how does it interact with the 660, look at the strain rate, where is it highest, what does the mesh refinement do, does it follow the slab well. You could even add some velocity factors to look at the flow field some more, as I write down here, and then think about how the boundary conditions might affect the flow field. And I will give you a few seconds for this before I discuss the results, and then I will also look at the chat because I cannot seem to do that. Chat, yes. Okay, I will continue with showing some snapshots of the model evolution. So down is an increase in time, and we look at the viscosity field just as what you were doing in ParaView. And then I have made this dotted line over here that indicates the initial position of the trench. And what we can see that we first have this short phase of trench advance, then trench retreat, and then at around 10 million years, the slab reaches the 660 and turns in on itself. I also ran this model in high resolution with the original thickness of the weak zone as described in the original benchmark, and this is what it looks like then. So there's a slight difference due to this resolution and shear zone, weak zone width. difference. What we can also do is have a look at the root mean square velocity over time, because this is printed in the log file, the statistics, velocity statistics, but also in the statistics file. And this you can find in the directory, the output directory, so it's called prescribed subduction. And you can plot it with Gnuplot again. And then we want to plot the root mean square velocity over time, so the second column and the 16th column. And what I wrote down here is just we divide the time in years by 1e6 to get millions of years, and we multiply the velocity by 100 to get centimeters per year. And in case you cannot get that to work, I made a little plot over here, which is what you should get. And now the question.
Can I ask a question? Can you explain the shorthand that you used in the plot there? The U, W, L.
Yeah. So plot statistics means plot the statistics file, and then the U is for using. So we use the second column. So versus, that is the column, the 16th column. And then because we want to manipulate, we want to do something with the entries in the column, we have to add this $ and put them between brackets, and then we can like divide them or multiply them with a factor. And then this WL is short for with lines, and that means instead of like separate symbols, connect the symbols with a line.
Awesome, thanks.
Okay. I don't see any questions in the chat, so I'm going to assume this works for everybody. And then which bit of the model is that velocity from? This is the root mean square velocity over the whole domain. So to the lower boundary. I will talk about that, what this lab is doing. So if we look at the root mean square velocity over time, together with what is happening in ParaView, what we can see there, then we can actually distinguish sort of three phases. And first, there's the subduction initiation phase, where the slab's being pushed in. This is what's driving the subduction. We're forcing the slab to enter the subduction, and this is paired with advance of the trench. But then when the slab has a significant amount of the plate hanging in the mantle, basically we have this enough negative buoyancy to increase the downgoing velocity of the plate. And this is where we see this increase in root mean square velocity. And this is also combined with retreat of the trench. And then after around 12 million years, the slab tip hits the 660. This is an impenetrable boundary in this model. And that because it reaches this boundary, the connection between the left side and the right side of the domain, because it's 2D, is broken. And then we have this boundary condition that actually prescribes a return flow. And this is one of the reasons why the slab turns in on itself. Another controlling factor on what the slab does at the 660 is also the shape and the viscosity of the weak zone. So you could also make the slab slide along the 660 depending on the shape of the weak zone. All right. Then in the actual benchmark, they tracked, among others, the root mean square velocity, but also some other quantities. I don't know what to call it. So there's, for example, the slab tip depth, which obviously increases over time, and also the transposition, where we can see first the advance and then the retreat. And our lower resolution, thicker weak zone model has a very similar evolution in terms of root mean square velocity as the original benchmark. So I just wanted to point out some things that can occur when you are doing subduction models. First of all, you can have diffusion after weak zone. The dependence of the results on the mesh element aspect ratio and the resolution of the weak zone. There can be a dependency on the averaging methods of for the composition, and the shape of the weak zone can also affect the model resolution. So that's something to be aware of. It's not particular to aspect, that is just something particular to these setups. And I just have one example. For example, if the weak zone is smaller but thinner at a lower resolution, you can see here in the viscosity, it's exactly the same model setup except for a thinner weak zone, that the viscosity, well, that the plates lock in terms of viscosity, so that there's not enough decoupling for the slab to go down, even after 15 million years. Okay, so if you want to extend on this model, you could definitely have a look at the grid resolution. You would add some temperature, advection, and a dependency of the density on the temperature. This would be case 2 of this benchmark setup. You could add additional layers in the lithosphere. You could change the rheology, add phase changes. I don't know, eclogite and the mantle transition zone. You could change to a free surface. You could have self-consistent subduction. Instead of prescribing the motions, you could just have it driven by buoyancy differences. And you could, of course, try in 3D. And I just wanted to mention that if you want to get inspired, you can always have a look at the list of publications, and also make sure to add yourself once you have a publication with aspect to the list. Then as an example of more complex setups, here is case 4 of the benchmark, where we actually use this viscoplastic rheology. And then an example of my 2018 paper, where we actually went to 3D and did a self-consistent subduction model. So instead of prescribing the motion, we have mid-ocean ridges at the sides, and we separate subducting plate and the overriding plate from this adjacent plate by a weak zone. And then we can look at the strain rate over time here on the right. And here it's also, again, very helpful to have the adaptive mesh refinement to, have the right resolution or enough resolution around the slab, but have a lower resolution in those areas in the mantle where we are not that interested in. Okay, then just another example from Menno's paper last year. This is a 3D setup of oblique subduction. I'm sure he will talk more about this tomorrow. And then this is a snapshot of half of the domain after 3.5 million years. And as a final example, I just wanted to mention this figure from Jonathan Roby's thesis from last year, where he actually looks at the volume of fluid method and the GG method and compares them, and shows that with the volume of fluid method, we can have the same results or similar results, but with one level of resolution less than for the DG method. And we can have 7 different levels of grid resolution to follow this crustal weak layer into the mantle. yes, and then I think if you would like to play some more with this model that we just ran, then the first thing to do would be to add an initial temperature field and make the density temperature dependent. And the initial temperature field would have an increase to 1600 Kelvin at the LEB, so at the lithosphere boundary, and then a smaller adiabatic gradient in the sublithospheric mantle. And you could do that using the function expression in line 90 of your parameter file. And I have one way to do that listed in the next slide that you could look up, but I will not put on the screen right now, just to not give you a spoiler. Yes, so this is all that I wanted to say about subduction model. And I don't know whether it's, yeah, I think we should have some time for questions now or a short little break, and then Juliana will take over.
And we have one question in the chat. Would this setup be suitable to model the subduction of a mid-ocean ridge?
Well, I would first go to something that is more like the case 4 of this setup, where and not stay with this very, very simple setup. But then, yeah, I think you could adapt it to subducting more. I don't know if Vinicius has doubts, like why, like what do you think could be problems with modeling this?
No, actually, it's just not because probably it will stop subduction because if we have an active mid-ocean ridge. So yeah, I'm just thinking about because I'm thinking to use these simple examples to put in the class for teaching. So yeah. But I have to get in to the codes and just try to implement something that could mimic or could actually just be part of any seamount or something that makes more difficult to subduct or something like that. Just to see in these simple setups. Just I'm thinking about that.
Yes.
But maybe it's better to get a case code for this specific problem, right?
So the problem I would see with a 2D subduction of a mid-ocean ridge is that you cannot transfer slab pull forces across the ridge, right? You would probably just subduct 1/2 of the ridge and then subduction would stop. So you would likely need a 3D setup that somehow transfers the stresses if the mid-ocean ridge is oblique compared to the subduction zone or something like this.
Yeah, I'm aware of some of these models of 3D with a threshold angle of 60 degrees. But yeah, we have a specific problem in the Brazilian geology, and I would like just to see these in a very simple 2D. Just trying to simulate subduction of a parallel to Trent mid-ocean ridge that I think is going to stop as well, but just to see that in a simple model. But thank you very much.
I have one comment that I'd like to make. So this setup and the 4 cases actually will be part of a series of cookbooks on subduction, because you mentioned doing it in class. So yeah, we will have a series of cookbooks on subduction using 2D and 3D, box and spherical geometries, driven and self-consistent subduction. I think some even with phase changes. And we've been working on this, but I think that should be finished this year. So that might be a good resource also to have a look at. Yeah, that's what I wanted to say.
And there was an interesting question from Bo, which you might want to address.
Okay.
It's a few up from Bo Zhang. It was about changing the weak zone shape and position through time.
Ooh, let me see that. Can we change the weak zone shape and position with time, like reading information from an ASCII file for different times? Well, I can say I have not done that before. I think it is possible to prescribe composition over time, but I have no experience with this, so maybe the other maintainers can say something about this.
Yeah, so I would say that basically depends on how you want to do that. So you can, so of course you can say, well, I make my composition just dependent on a sort of function that can depend on time. So you could say I make a new material model that has a function that says, well, at this and this position and that could change through time, I want to have a weaker part of the model. But then that's no longer the same as a compositional field. So if we use something like a compositional field, that means we start with a given initial distribution, and then the compositional field, so the position of the weak zone also changes, right? It's like it vectored with the flow, and so depending on like how much the other parts of the model move around, the position of the weak zone would also change. And you have to decide which of those two you want. So you can either say I want to prescribe where that weak zone is, or you can say I want to self-consistently let it evolve with the model. And so both of these would change the position over time, but and usually what you want is the second one where everything evolves self-consistently.
Yeah, there have been some people in the community who, especially if you're not using a free surface, who prescribe the weak zone position basically. And and I think even though the model is time dependent, they basically independently prescribe that weak zone position. But that can lead to all sorts of other complications and weird things happening with the dynamics locally around the weak zone. So I would agree with you, Juliane. The best thing is to have things evolve dynamically. Will probably lead to much fewer problems over time. That's a bit more realistic as well.
Yeah, I think I've also seen setups where the motion of the weak zone is prescribed, or the motion along. So there's an internal boundary condition basically for the subducting plate over time, where they prescribe the velocity of the surface of the slab inside the model domain. So this is another way of forcing the model. But like Juliane said, I think in general you want the model to evolve freely over time.
I tried at some point, so some of Tarascuria's models and people from his group sometimes initiate subduction with those internal boundary conditions. And I tried that at some point, but there were all sorts of issues with the nonlinear solvers. So then maybe this works okay with, if it's a simple linear system, but I tried this for a couple of weeks and had no luck. So I would suggest Juliane and Anne's suggestion to go with the dynamic approach and the approach Anne has shown here. In the end, it leads to much fewer complications.
All right, so are there any other questions or anything that we should discuss regarding to this problem? So because I would say if there are any more questions about subduction in general, we can talk about them now. And so I would say we'll just wait for a minute or so to see if there are any other questions. If there are no other questions, I would say let's take a break right now for maybe like 15 minutes or so. And what you can do is, Anna had a number of suggestions for like how you can change the model, so how you can make it more realistic. So if you want something to do in the break, then you could open up that slide and try to start changing those things and playing around with the model a little bit. So yeah, so I don't see any other questions right now. So I guess I would say let's take a break. And in the break, you can play around with the subduction model a bit, and we come back at, so like at the hour, or I guess in India, that's like 1/2 the hour.
I'll put that slide back on the screen just for the break.